This is a tutorial on complex numbers and DeMoivre's theorem. Typically, when we talk about complex numbers, we write them in a form that looks something like this: a plus or minus bi, where I is equal to the square root of -1. We talk about complex numbers because you cannot take the square root of a negative number. So if I had 5 plus the square root of -49, I would have to use my properties of powers to split this up into the square root of -1 times 49. And then I would split it up into the square root of -1 times the square root of 49. Now the square root of 49, that's 7. And I can't take the square root of a negative number, which is why I removed this square root of -1, because I'm just going to call this I. So in this case, my imaginary number, or my complex number, is 5 plus 7i. My a is 5, and my b is 7. This 5, or this a, is called the real part, and this b, which is multiplied by I, is called the imaginary part of our complex number. Now typically, if we want to plot a complex number, we plot it on a rectangular axis where the x-axis, or the horizontal axis, is the real axis, and then the y-axis, or the vertical axis, is our imaginary axis. So if I have a plus bi, or 5 plus 7i, then my imaginary number z, instead of saying it's a plus bi, I could say that it's x plus yi. And in this case, x, or my real part, is 5, and my imaginary part, y, is 7. Or you can think 7i. And if I wanted to plot this, I would go along the real axis, my real part, or in this case 5 units, and then I would go up along the imaginary direction, or the imaginary axis, my y part, or 7, to this point right here. This is the point z. Now when you take the absolute value of an imaginary number, or a complex number, remember that the absolute value is the distance that point is from the origin. If we were taking the absolute value of 5, well, that's just 5 because it's 5 units away from our origin. If we want to find the absolute value of a complex number, though, we would want this distance. This distance is the absolute value of z. Now, if I want to find the absolute value of z, I can think of this kind of like a triangle. And then I can use the distance formula, or I can use Pythagorean's theorem, because this is a right triangle. So I take my x part and I square it, and I add that to my imaginary part, or my y part, which is also squared, and I take the square root. This is the square root of 25 plus 49, or the square root of 74, which, if you're curious, is about 8.6. Well, you may notice that finding the absolute value of our complex number is a lot like converting our complex number into a polar coordinate system. If I said this absolute value of z, that would also be distance r, and then all I would need is a theta value. Remember, when you convert from rectangular to polar coordinates, this x value here this is always equal to r times the cosine of theta, our hypotenuse length times the cosine of this angle. And then our y value, this is always equal to r times the sine of theta. But remember that we're going in the imaginary axis. This is not the y-axis, this is the imaginary axis. So even though I'm calling this y, this is really r sine theta times I, times the square root of -1. So if I wanted to, I could take this form, and I can say z is equal to r cosine theta plus r sine theta times I. This is x. This is y. And if I factor out an r, I'll get z is equal to r times the cosine of theta plus I sine theta. Well, this is how you write complex numbers in polar form. If I wanted to find theta, I could use the tangent function because the tangent is just the opposite side length over the adjacent side length. So the tangent of theta is equal to y over x. Our y is 7 and our x is 5. So the tangent of theta is 7 over 5. Put that into your calculator and find that theta is about 54.5 degrees. So if z is 5 plus 7i, I could write that as the square root of 74, because that's my r value, times the cosine of 54 degrees, or 54.5 degrees, plus I times the sine of 54.5 degrees. So let's try this again. Let's write a complex number in polar form. Remember, normally it's z is equal to x plus yi. When we want to make it, z is equal to r times the cosine of theta plus I times the sine of theta. So let's convert z is equal to 5 plus 6i into polar form. Now it usually helps to first draw a triangle. The bottom of my triangle follows the x, or you can think of the real axis. And this length here is 5. This side of my triangle follows the imaginary axis, or you can think of that as the y-axis. And then this length is 6. So if I want to write this in polar form, I'm going to need an r value and I'm going to need a theta value. Well, to find my r, I'm going to take the absolute value of this number. So I'll have the square root of 5 squared plus 6 squared. This is the square root of 25 plus 36, or you can think of that as the square root of 61. So this is our r value. If you're curious, this is about 7.8. So we have our r value, and we're going to need our theta value. So I'm going to use the tangent function to find that. Remember, the tangent of theta is equal to opposite over adjacent. So the tangent of this theta, the opposite side length is 6, and the adjacent side length is 5. So the tangent of theta is equal to 6 over 5, and if you plug that into your calculator, you'll find that theta is about 50 degrees. So I have everything I need to write this in polar form. So z is equal to our r value, which is the square root of 61, times the cosine of 50 degrees plus I times the sine of 50 degrees. Now, if you don't want to remember this formula, you can always remember the conversions from rectangular to polar coordinates. You can remember x is equal to r cosine theta and y is equal to r sine theta. And then you can plug these values in for x and y, and you'll end up with the same number. So now let's try going the other way. Here we have a complex number written in polar form, and we want to write it in the rectangular form that we're used to. Here z is equal to 7 times the cosine of 60 degrees plus I times the sine of 60 degrees. Well, usually I like to start by drawing a triangle. It doesn't have to be to scale, it just has to help me see what's going on. Now, when we're written in complex or polar complex form, z is equal to r times the cosine of theta plus I times the sine of theta. This distance is r and this distance is theta. This distance is y and this distance is x. Well, I have my r value. R is 7, so this is 7. And I have my theta value, that's 60, so this is 60 degrees. Now, using the sine function, remember that sine of our angle is equal to the opposite over the hypotenuse. This is a right triangle, so the sine of theta, which is 60 degrees, is equal to the opposite side, which is y, over the hypotenuse, which is 7. So y is equal to 7 sine 60. And this is equal to approximately 6.06. For my x value, well, I know the cosine of theta is equal to the adjacent side length over the hypotenuse. So the cosine of 60 degrees is equal to x over 7. So x is equal to 7 times the cosine of 60 degrees. And we'll find that x is equal to 3.5. So I have my x and my y value, but remember, this isn't a normal x and y. This is actually the real and the imaginary axis. So that means z is equal to 3.5 plus 6.06 I. Because remember, complex numbers in rectangular form look like z is equal to x plus yi, or a plus bi. Here our x is 3.5, or our a is 3.5, and our y, or our b value, is 6.06. Just don't forget to include our I for the b or the y value. So now let's talk about taking the product of complex numbers. Normally, if we had a plus bi and we multiplied it by c plus di, we would have to FOIL this out. Well, when our complex numbers are written in polar form, say complex number 1 has a r value of 1 and a theta value of 1, so it's written in this form. And our second complex number, z2, that has a different r, so we'll call it r2 and theta 2. So if we want to multiply z1 and z2, we just multiply their r values, and then inside the cosine we add the theta values. And then inside the sine we add the theta values. So let's multiply these two complex numbers in polar form. z1 is equal to 4 times the cosine of 45 plus I times the sine of 45. z2 is equal to 2 times the cosine of 240 degrees plus I times the sine of 240 degrees. We're multiplying, So z1 times z2, I'm going to use my formula, is r1 times r2, so 4 times 2, and then times the cosine. Now I add my angles, so 45 plus 240. And then plus I times the sine of 45 plus 240. So z1 times z2 is 4 times 2, which is 8, times the cosine of 45 plus 240 is the cosine of 285 plus I times the sine of 45 plus 240, 285. And that's how you multiply two complex numbers written in polar form. So now let's talk about dividing complex numbers, or the quotients of complex numbers. Well, this is just like multiplying. Instead of multiplying our r values, we're going to divide them. And instead of adding our theta values from our two numbers, we're going to subtract them. So if we're dividing z1 by z2, then you're dividing r1 by r2, and you're subtracting theta 2 from theta 1. So let's practice this. We have z1 is equal to 10 times the cosine of 30 plus I times the sine of 30, and z2 is equal to 4 times the cosine of 305 degrees plus I times the sine of 305 degrees. z1 divided by z2, that's equal to r1 divided by r2, so 10 divided by 4, and that's multiplied by the cosine of 30 minus 305 plus I times the sine of 30 minus 305. So z1 divided by z2, 10 over 4, you can think of that as 5 over 2. And that's multiplied by the cosine of, now 30 minus 305 is a negative 275 degrees, plus I times the sine of negative 275 degrees. Now, this is an acceptable solution, except I don't usually like to have negative angles. If I start here and I go in a clockwise direction or a negative direction around to 275 degrees, I can find a positive angle by going the other direction. If this is 275, then this is 85. So I'm going to write this as z1 divided by z2, and that's equal to 5 over 2 times the cosine of 85 degrees plus I times the sine of 85 degrees. And that would be our solution. So now let's talk about DeMoivre's theorem. If I have a complex number written in polar form, z is equal to r times the cosine of theta plus I times the sine of theta, and I want to raise z to some power, n, then instead of multiplying z times cosine theta plus I times the sine of theta by itself over and over again, I can use DeMoivre's theorem, and that tells us that our complex number raised to the n power, well, that's the same as r to the n power, and then the n comes inside our cosine and our sine, and we just multiply our angle by n. So it's the cosine of n times theta plus I times the sine of n times theta. So again, let's practice this. Here's DeMoivre's theorem. Here's z. It's equal to 7 times the cosine of 20 degrees plus I times the sine of 20 degrees. And we want to find z raised to the 4th power. Well, z to the 4th power is equal to r to the 4th power, so 7 to the 4th power, times the cosine of n times theta, so 4 times 20 degrees, plus I times the sine of 4 times 20 degrees. So, z to the 4th power is equal to 7 to the 4th power, which is 2,401, and that's multiplied by the cosine of 4 times 20 degrees, or 80 degrees, plus I times the sine of 4 times 20 degrees, or 80 degrees. And that would be our solution. So now let's talk about finding the square root of a complex number, or at least a complex number written in polar form. Now remember, if I take the square root or the second root of some number, say 4, I always end up with 2 solutions because this can be plus or minus 2. Well, when we find a complex root, if we have the nth root, we have n possible solutions. So if I'm taking the 4th root of z, I'm going to have 4 solutions. If I'm taking the square root of z, I'm going to have 2 solutions. Our formula for doing this, if I have the nth root of z, then we just take the nth root of our magnitude or our r value, and then it's multiplied by the cosine, and we divide our theta by that n. But then to get the other solutions, we add 2 pi over n, and then multiplied by k. K is this integer. Our first solution to our root, k is equal to 0. For the second solution of our root, k would be equal to 1. For the third solution, k would be equal to 2, and so on and so forth, until we find all of the solutions for our root, all n of them. So if n is 4, there's 4 solutions. We do the same thing for the sine. Take our original angle value and divide it by n, but then we add 2k pi over n for each additional solution that we need. Now, if you're not measuring in radians, realize that you don't need 2 pi here. Instead, you would be adding 360 times k over n. This 2 pi just represents one rotation around the pole. So if you're measuring in degrees, one full rotation around the pole is 360. So let's try a practice problem. Here we have our formula, and we want to take the 4th root of z, where z is equal to 10 times the cosine of 60 plus I times the sine of 60. So, the 4th root of z, well, that's equal to the 4th root of r, which is 10, times the cosine of theta, which is 60, divided by n, which is 4, plus, now I'm not going to use 2k, I'm going to use 360 because we're measuring our angle in degrees. So plus 360 times k, which for our first solution is 0, over n, which is 4, plus I times the sine of 60 over 4, theta over n, plus 360 times k, which in this time is 0, over 4. And this is our first solution. Simplify it a little bit. The fourth root of 10, that's 1.78 approximately. 60 over 4, that's 15 degrees. 360 times 0 is 0. 0 divided by 4 is still 0, so we have the cosine of 15 plus I times the sine of 15. And this is our first solution. Now we're going to end up with pretty much the same thing for our second solution, except our angle is going to be a little bit different. If we take this part or this part, they're the same. For our next solution, our k value goes up to 1. So this is going to become 60 over 4, which is 15 degrees, plus 360 times 1 this time over 4. 360 times 1 divided by 4 is 90. So 15 degrees plus 90 degrees, that's 105 degrees. So our second solution is 1.78 times the cosine of 105 degrees plus I times the sine of 105 degrees. For our third solution, our k value goes up to 2. So again, we have 15 degrees, 60 over 4, plus 360, this time times 2 over 4. This is equal to 180. So I have 15 plus 180, which is equal to 195. So my third solution for this root is 1.78 times the cosine of 195 degrees plus I times the sine of 195 degrees. One more solution to go. For my fourth, I go up to k of 3. So 60 over 4 is 15 again, plus 360 times 3 this time over 4. 360 times 3 and divided by 4 is 270. So 15 plus 270 is 285. So my fourth solution is 1.78 times the cosine of 285 degrees plus I times the sine of 285 degrees. So these four complex numbers in polar form are all solutions to the fourth root of z. And now that we've figured out how to find complex roots, that completes the tutorial on complex numbers and DeMoivre's theorem.